building imitation module and the module imitating the Martian terrain. All the modules, except for the latter one, are hermetically sealed and equipped with the individual life support system. A great number of volunteers from different countries were inspected at the Institute to select the members of the experiment. The principal indicators under investigation were medical ones: good health and the absence of pernicious habits, psychological stability, and the level of professional skills. Physicians, engineers, and biologists were among the most sought-for professionals that will be selected for staying in the conditions of long isolation and carrying out different experiments that will be ordered to them on board the module. A crew of 6 will be formed out of the volunteers who passed the testing. It will make a virtual flight to the Red Planet. Prior to their isolation, the volunteers will have medical and scientific training. The project aims at investigation of the man-environment system and obtaining experiment-based data on the state of health and working capability of the crew in the conditions of isolation in a totally hermetical closed space of limited dimensions and in the conditions of basic specificity of a flight to the Mars. A very long flight, autonomy, irregularities in communication with the Earth causing delays in establishing contacts and reliance on limited resources. Other tasks of the project are an attempt to verify the possibility of such a flight from the psychological and physiological vantage points, as well as working out a set of requirements for a real expedition to the Mars. At present, the Institute of Biomedical Problems is completely prepared for arranging an imitation flight to the Mars, including the crew's walk-out on its soil. It will be maximally close to reality.
Dear colleagues, I don't have too many comments, actually, and I don't want to jinx anything here. The experiment that had just started shouldn't be discussed at length. There were so many years that went into the preparatory work, for this experiment. And right now the preparation stage is over. On June 3rd, there will be isolation that starts. And frankly, I should be in Moscow. I should be at home right now. And I should be participating in the continuation of this preparatory work. But I did want to visit here very much. I wanted to participate in this summit. And this presentation was made especially for you. Totally, there will be 105 scientific experiments in this project. Each one of them will represent a significant unit of various parameters, assessments of various duration, different importance, different approach, methodical, procedural approaches. I'm not going to list all of the experiments. They are on the site, on our website of our project. But I want to say that we're very grateful to all the European and American scientists and Chinese scientists who have contributed, who have participated in this program. The crew has been selected. It consists of 2 representatives of European Space Agency, France and Italy, 1 representative of China, and 3 representatives of the Russian Federation. At this particular moment, there are 4 of them, but 1 of them is in reserve. The experiment itself is extremely difficult. It's not going to be a cakewalk. As you saw in the beginning of this plot, even with all the positive results that are envisioned, there were no conflict situations during the previous stages of the experiment, but the psychological and physiological methods that were applied during the experiment have demonstrated that there were some changes in the subconscious sphere. There were certain changes that were characterized by that characterize brain as a system that is in the state of alert or anxiety. At times, in certain intervals of time, in those times when psychological support was required, when there was a boundary case that bordered with the initial stages of depression. And in other words, the changes are very peculiar, and those changes testify to the fact that this is a stressful environment. And although it has trace nature and its traces are felt sometime after the experiment, one can expect that the 520-day experiment is going to be more complicated, and perhaps the greater degree of risk is involved in terms of changes in various systems of the human body. So we were careful in our approach, and that crew that was there at the end of this plot, it has undergone many different phases of medical investigation and selection. And we're hoping for the experiment to be successful. We're also hoping that all the 105 programs that are planned will be performed, completed, and that we will obtain very important data on virtually all of the psychophysiological factors. There are around 20 of them, and we're going to try and simulate them in the experiment. Of course, there will also be simulated certain contingency situations. For instance, this is an open system. The simulation is open, and we're open to your proposals. So we're expecting certain proposals, and our administrative board is going to review that. And it's possible that at certain stages of the experiment, we'll be able to implement those proposals in the entire system of the experiment. But of course, we would prefer for them to be very carefully weighed, and that they would not perturb a very complicated structure of the experiment. So this is all I had to add wanted to present for you. The experiment should start on June 3rd, as I've already mentioned. We're counting on cooperation, and I'm also thinking, as it was proposed today, if we make ISS 500, then we're going to have a virtually entire complex or so-called bouquet of impacts and effects of sun's radiation that will allow us to conduct experiments on biological, including the biological study, not human subject research. So in a few years, we'll be able to draw certain conclusions on the possibility of the Red Planet expedition. Thank you.
Let's go ahead with the next panel, and I'd like for the panelists for the International Interdisciplinary Integrated Collaborative Research in Space to come forward and take their seats at the table. We're very fortunate to have Dr. Neil Lane as the moderator for this panel. Dr. Lane is the Senior Fellow of Science and Technology Policy at the Rice Baker Institute. He's well known, I think, to almost all of us because of his roles, not only at Rice over many years, where he served as provost, and then in Washington in the White House Office of Science and Technology, and with the National Science Foundation Academy. So, Dr. Lane?
Thank you very much, Bobby. Welcome, everyone. I'm very pleased to be a part of this exciting program, and of course, especially honored to moderate this panel. My only experience with the many important matters we're talking about here in space in general is currently my work with George Abbey here at the Baker Institute. I was a science advisor to President Clinton during the time we finally began to, with our international partners, beginning with Russia, began to put together the space station. So it was very exciting for me personally to be able to report regularly to the President and this White House staff on this exciting project, which of course we proudly have talked about as the greatest international technological achievement of all time. And history will show what an extraordinary accomplishment this has been. And I think the even more exciting things are coming in the future, and much of that we'll talk about today, and tomorrow and through Sunday. So I'd like to just let the panelists introduce themselves, starting with Mr. Chin. Of course, many of you know the panelists, but not everybody has been here for every event. So if you don't mind, let's just go down one at a time and say who you are and where you are, and then we'll take brief remarks.
Thank you. I'm Shan Guangchen from ECC, and this morning I gave brief comments on brief descriptions of my centers. I think that Mars 500 is a very important international cooperation project, and it's also challenging and of great significance. Despite of the limitations of the ground simulation, but we also have a lot of research items or projects to be carried out. And in this project, one of scientists is from my center. as the director Ushakov just told, that a young scientist from ACC was selected and determined as one of the crew members for this experiment. He's about 28 years old and is a doctor. Is responsible for the medical monitoring and medical care for the astronauts in China. He's single, unmarried at the moment. So maybe it's for him it is a very difficult time in 500 days. We also have some experiments with two aspects. One is to examine some psychological effects or social effects for the crew members. Another one is some Chinese medicine treatment, which is, I'm sure it is the first time for the Chinese medical medicine treatment is used in or adopted in the ground experiment. We have developed a very special device according to the Chinese medicine theory, and to collect some psychological or physical data in Chinese way. I think will be very important for the later research and the process of the processing. So I believe that we will get or we will obtain much more results or achievements from this kind of experience or the international projects. And I also hope that we will have more chance with such kind of international cooperation. Thank you.
Clark.
Good afternoon. My name is Jonathan Clark. I'm the Space Medicine Advisor at the National Space Biomedical Research Institute. The main role I function in is to help integrate research from lower technology readiness levels, the more basic levels, using analogs as test beds to get them through to higher levels, and then eventually translate them into operations. This is a process that's absolutely necessary for all those involved in space research, and one of the major components is to understand that it's not just the research, it's the development, test, evaluation, and the operational integration. And one of the things I've been quite proud about is to be involved in our user panel, which Dr. Leroy Chow chairs. And the goal there is to get actual operators, astronauts, and flight surgeons who evaluate research proposals before they're actually approved, help with the solicitation, research requests for research proposals, and then actually along the way help to formulate how to get them into an operational setting. And I look forward to the discussions for this afternoon session. Thank you.
Okay, good afternoon. My name is Volker Dahlmann. I'm head of the Crew Medical Support Office at the European Astronaut Center of the European Space Agency in Cologne, Germany. Have been a flight surgeon for quite a long time, trained at the German Aerospace Institute. So Professor Gerzer was my boss some years ago. And then went to ESA. Well, similar to John, I'm trying to look into what are the enabling factors to promote spaceflight, human spaceflight in the future. And if you enter this institute, there are 3 doors, and above the leftmost one, there's this beautiful sentence that says a bridge between the world of ideas and the world of action. And I think that says it all. That I think is the theme also of the meeting here today. And I'm very much interested in seeing how we can merge the fields of life science research and basic research and applied research and the knowledge that we have gained throughout the support of human spaceflight in the past. And I have to admit I'm a Star Trek fan. And that's not, and I think we should sometimes very much look very seriously into technologies and developments that you see in science fiction, but at least have a closer look if maybe they're not that far away. And I think we learned that during the lunch talk, that sometimes it's very helpful to look across and not only stick to your own field of science and technology, but be so just looking across and trying to find an answer in different fields. So that's my prime task, I think, for the next couple of years until my retirement, to advance space medicine, the knowledge, and to enable the next generation of humans to going into space.
Well, ladies and gentlemen, my name is Rupert Gerzer. I'm head of the Institute of Aerospace Medicine at DLR in Cologne. Now, our institute has in space about 100 people, and we do a lot of experiments in physiology, radiation work, astrobiology, and also we have crew surgeons who support ESA, and also take care of some facilities in the Columbus module, like the biolab facility. Now, one of my major roles is to convince the people who are involved in giving us money to spend money in human spaceflight. And maybe afterwards, in the second round, I will focus a little bit on this task. Inside this task, we are currently on the way to build a new research facility. Thank you. And I'm editor-in-chief of Acta Astronautica and hope to motivate all of you to submit to this journal and to get good papers into this journal.
Good afternoon. My name is Dennis Grounds. I'm the NASA's program manager for the Human Research Program. And the goal as an agency is to reduce the risk to humans in spaceflight, in particular for exploration missions. Within the Human Research Program, we cover the topic areas of radiation, space human factors and habitability, behavioral health, medical technologies, and radiation. So we cover all of the disciplines and map all the risks and attempt to reduce the highest risks according to the exploration missions. Thank you.
Hi, I'm Vadim Gushin from Institute for Biomedical Problems. I'm social psychologist for the 20 years participating in the space simulations and the chamber studies all over the world, let's say. Have some experience and trying to be short in comparison with the previous Russian speakers. I just want to stress one point. Just one small point. The idea of Dr. Dinges is the idea which is interested not only, I think, to the psychologists. This is the idea of making the international research teams. We are good in team building for the space crews, more or less. But as for me, and from that point I support the speech of Academician Kozlovskaya, that we are not good in making the research groups analyzing the important sides of the scientific phenomena in space and here on Earth related to space. And this is the major concern. Our director, Shakov, informed you about 105 studies. And I think it's an advantage, of course. It gives you the overview that many issues will be investigated. At the same time, it gives the point that there is no, for example, let's say, overall psychological program, international in Mars 500. There is no overall physiological program. There are separate studies where all of us feel like mice taking our grain and hiding in the hole somewhere. And from that point, Lauren Leventon last December made a very nice presentation in Noordwijk devoted to the assessment of quality of simulation studies. And this is a very nice presentation and very nice idea to evaluate the quality of the research infrastructure. And from that point, I think we're not at the top level. We are not in space. And this is my major concern as for now.
I already introduced myself in the first part of today's meeting. My name is Dr. Kozlovskaya. I am from the Institute of Biomedical Research, the same as Dr. Gushin. And I am head of the Department of Sensory Motor Physiology and Countermeasure. That's its precise title of the lab. And during long-term stay at the IBMP, I was participating and even organizing some of many international experiments which were performed on Mir station. They were, our institute has a very great experience in international cooperation. There were great programs starting from French program on sensory motor, which lasted for many years, and the Russian-Austrian program on neuro and sensory motor as well, which also lasted for 10 years, and even Russian and American, Mir-NASA, which lasted also about 10 years. And of course, during that time, we acquired great experience and great hopes in international studies. And we were very hopeful, and we when we started ISS program, and we continue, of course, our cooperation. When scientists start to cooperate, they do cooperate if they are interested, if they have trust. Like today, the lector, excellent, told us what is necessary for cooperation. We know that we have everything for this cooperation, and skills, and trust, and wishes, and ambitious, and everything. But somehow, we see that this cooperation doesn't go properly, and I think it is our challenge for the very close future to develop it. Otherwise, the results of ISS of 20 years will also not satisfy us to the full extent.
I'm Julie Robinson. I'm the International Space Station Program Scientist for NASA here in Houston. And so the perspective I bring on research collaboration is one from working day to day with my international counterparts who are the chief scientists for their respective agencies on the space station. And that perspective is grounded in what I think is the most extensive research collaboration that we have ever had in space. It's just a collaboration that's warming up now with 10, maybe 15, maybe even more years to go in that research collaboration. And already we've learned important lessons from that collaboration. Thank you.
Добрый день, меня зовут Владимир Сычев.
Good afternoon, my name is Vladimir Sychov. I represent IBMP, where I had biological life support laboratory. My science background is such that space experiments that I started working with was Inner Cosmos program, then it was Mir NASA program.
I believe that space experiments are unique in a sense that they're very expensive, and the more we can cooperate and work together, the better results we get. And so our international cooperation is one of the key elements that would allow us to reach success in our space studies and exploration. In ISS right now we have two separate programs, Russian and international. These two programs have very little interaction. However, despite that, we're able to have international cooperation. We are working together with our US and Japanese colleagues, and despite the situation that we were faced with, we continue this long tradition of international cooperation, and because of that we have great results. And once again, it is international cooperation that is the key to our success as a program.
Thank you very much. Do panelists have additional comments now that we've heard a little bit from everyone? If not, we'll have yes, please, would you like to make additional comments?
Sure. Well, I'm from Europe, from Western Europe. In Western Europe, we have no own human spaceflight system. We participate in human spaceflight. The Americans have a system, the Russians have a system, the Chinese have a system, and we have no system. And this is a big difference, because when I say we go to the space station to develop countermeasures, my government will say, why do we do this? Let the Americans or the Russians do it. When we say we do a Mars analog study, Mars 500, and I say I want to participate, my boss likes it, but the government does not like it, because they say, why fly to Mars? We don't have a system. Let the Americans and the Russians spend their own money. Why should we Germans always pay? So, and we are in Europe. When we look to Europe, Germany is paying 40% of the budget for the European participation in the International Space Station, and all the other European countries are either shaky or not participating at all, like the British. We are paying. So my argument has to be different, and this I want to feed into our discussion here. We cannot say, I am very excited about all those things, but we cannot argue in this way, because we need to sustain our funding. And therefore I think we need, in Western Europe, we need to convince by other reasons. And the other reasons are, what are the unique features of space medicine that we can contribute, where we can add something to our society. And I think I have a few points which have so far been convincing, because fortunately our budget is increasing, although the political support so far is not yet increasing, and we hope to get more support. The first thing is countermeasure development. When we say we develop countermeasures to develop countermeasures, we have lost. When we say we develop countermeasures because we made a risk analysis, we have lost. But when we say we develop countermeasures because we need countermeasures only because we have not understood something in physiology. If we would have understood physiology, how somebody who lies in bed behaves, what his problems are, we would not need to develop countermeasures. So the countermeasure development itself is a scientific question. And countermeasure development only tells us we have not understood something, and as soon as we find the proper countermeasures, we hopefully have understood something. So countermeasure development, we completely can participate, but only our argumentation has to be the opposite way around. And countermeasure development means research, and also basic research, because we have not understood something in basic research. It occurred to us, for example, studying in salt balance, that we found out suddenly salt balance is not really understood. I had learned in medical school 30 years ago or 40 years ago, we know about salt balance. And now it turns out we have forgotten something, and it turns out if you eat a lot of salt, you decrease a lot of bone mineral density and so on. And it suddenly turns out salt balance has a lot to do with the immune function and with the macrophage functionality. All new areas in medicine which I think would not have come if we would not do basic research in space. So we should really follow what also NASA and NIH is doing, to say the ISS is a research laboratory, and we should not distinguish between space research and terrestrial research. Questions are questions and research is research. You cannot just separate, number one. The second thing which is a real asset of what we have, we have to study the whole human. And we have the possibilities to study the whole human. We can only study the whole human if we do collaborations and international collaborations. Nobody else in medicine really can do this and does do this. And therefore, we have to really be strong in this and propagate this. And the third thing is we have analog studies. Coming back to the Mars 500, I can fascinate my funding agency when I say Mars 500 is a unique possibility for medicine. For example, when we look to blood pressure and salt, we all learned in 30 years if you eat a lot of salt, you get a high blood pressure. But nobody has studied it. It has not been demonstrated. There are many, many, many small studies, but nobody ever has the money to study influence on salt in a well-controlled study within up to 500 days. It's a huge opportunity. And so on. So there are many, many features which can be added into normal medicine when we do our analog studies. So the analog studies are great and fantastic, and we should focus on the advantages and possible advantages for medicine. And the fourth advantage is it's unique. We can really fascinate the public, and we can do education and outreach and use what we are doing for education and outreach. And because of those reasons, fortunately, DLR is investing in a huge new research facility which will focus on those advantages. Always saying, okay, we use spaceflight problems, but in order to solve problems and questions on Earth. And also to have a possibility for analog studies and also have a possibility for the public outreach. So to end, I would really like to ask you not to forget the science side of the countermeasure development. Thank you.
Thank you. Further comments? Yes, please.
Neil, many of you may know some of the things I'm about to say, but this is, I thought it would be important to review some of the mechanisms that are in play for international, interdisciplinary, cooperative research. These are mechanisms, many of which have been in place for years, many of which are highly effective. The first is the International Space Life Sciences Working Group, which involves all of the International Space Station partners, plus some national space agencies from France and Germany, as well as the Ukraine. That particular organization has been responsible for a framework agreement that allows us to share and share alike the hardware, the major hardware items on space station in a cooperative manner, so that we did not have to each build copies of central type devices, things that would take crew weight, mass spectrometers, the main instruments for human research on space station. That's been 16 years of cooperation. It's resulted in tens, if not more, cooperative experiments that have gone on both in flight and on the ground. It is a very active group, meets twice a year, and still formulating cooperative experiments to this day. Our joint activities with our Russian partners through the Joint Working Group, which has been a long-standing relationship over 30 some odd years, predominantly winds up having collaborations between scientists, individual scientists working on similar areas. And in that way, we've conducted many research experiments associated with space flight, and I could name a few, but there were that particular activity goes on at least annually, and has been quite fruitful. It hasn't been everything that I think this group has talked about in terms of coming to standard measures and standard experiments for both in-flight and post-flight evaluations of crews, but it has resulted in some very specific and important cooperative studies. Thirdly, in looking at the future, there's an international countermeasures working group, which Dr. Kozlovskaya and others are members, in which we are, as I think she mentioned earlier, defining the exact content of standard protocols for pre-in and post-flight. It is true that we have not implemented that completely, but that work group has been working for 3 years, looking at what parameters need to be measured and how they need to be measured. There is, as Dr. Davis mentioned earlier, now, as a result actually of this meeting last year, an international human system risk board that meets every 3 months to talk about the risks of spaceflight and agree internationally on the degree and consequence of those risks. I thought it was important to review for you the mechanisms that are available and those that have worked, those that are working, and I would like for you to keep in mind, though, that this process, as our speaker at lunch talked about, these take relationships that bear time to get to know each other, to find the common areas, to trust each other, to learn how to share data, and that's what's happened in many of these groups.
Thank you very much. Further comments from the panelists, please.
If you allow me, I'd like to inform the audience about Mars 500 a little bit more. I just want to specify 3 important features which were not observed before in the previous space simulations and even the space flights. First issue is the high autonomy factor, which is not the case for the orbital flights, when the crew can get resupplies and therefore they can get whatever they want, maybe not when they want, but what they want. High autonomy is about the interplanetary missions, about the planetary bases, when the group there will have no resupply, will have to use only their own resources. And by resources, I do not mean logistics only, but I mean knowledge, I mean skills, I mean awareness how to deal with the problems. And this is the first issue which will be for the first time deeply analyzed in Mars 500. Second issue is related to the landing, because all the chamber studies or for example, polar wintering, or that brilliant NEMO mission, which is a very nice analog from the point of view of risk and real performance. So landing is the new, let's say, kind of operations. It's not just one operation. It's the set of operations related to many issues, psychosocial issues, to the issues related to the influence of microgravity on performance, to the changes of adaptation to the different level of weightlessness, and many other issues. But first of all, it's about how to simulate landing. Not to pretend that you land, but to simulate. And this is a very interesting research area which we're trying to open, let's say, in Mars 500, and this is absolutely new and very interesting from different points of view. And finally, this is about cross-cultural study. Being a psychosocial psychologist in the area of cross-cultural relations, I'm especially interested in the influence of cultural barriers which maybe did not yet showed themselves on ESS, but will definitely be a problem in the long mission to Mars. And from that point, the issue of participation of the Chinese and 2 Europeans in Mars 500 is not just the political issue, but the issue which will allow us to understand how different cultures, so different like Asian, European, and Russian culture could interact, and how much this barrier will be, how high it will be for us. And from that point, again, I want to stress that Mars 500 is unique, and it's the big step forward. And we are not just, again, pretending to do something. We are really trying to simulate the real flight, the real mission, and very significant aspects of it. Thank you.
Thank you. Other comments, please. Please,
yeah, to follow up what Professor Gatza mentioned, he has to deal with one agency and one country. ESA has to deal with 18 countries and 18 agencies. So that makes things not necessarily more easy. That's the downside. The positive side, though, is that I think it's custom in Europe to integrate, to collaborate across the different teams. Because that is Europe. That's what Europe is all about, with the different cultures and the different labs and the different institutions. The term interdisciplinary that shows up on the heading of this session, that is something where I think we have to get much better. It has been accustomed to separate life science and medical operations and medical care. And I think there we are growing together. We have to grow together. And as Jeff Davis alluded to this morning, we have to understand the astronaut norm. We have to understand what is the physiology, the normal physiology of our astronauts when we want to further explore. The European, and ESA is not even the European Union. Most of you may not know that. The European Union, different member states than within ESA. And there are sometimes even conflicting programs within the European Union and what ESA has in mind. But at least just recently, the European Science Foundation launched an exercise, and Rupert and myself are members in that group, to identify across the different entities that define space medicine, the roadmap, the European roadmap, so similar to what NASA has done already many years ago, but at least to identify what are the areas of science and operational scenarios that we need to understand to promote human spaceflight in the future.
Julie Robinson.
Thanks. I wanted to expand a little bit on what I think are philosophically some of the things that we've learned from the space station so far in international cooperation. The first is that we have learned that we can collaborate, and collaboration is critically important, but that's very different than oversight. Because oversight implies a central authority, a central agreement, and that stifles scientific creativity, and it eliminates many opportunities for scientific discovery. So we work together to coordinate, to optimize, to collaborate, but never to control. And I think that's a very important point. By maintaining a diversity of research objectives across the different partners on space station, we have many more opportunities for discovery, because of course scientists can generate many hypotheses, but they never know which one of those is going to turn into a real discovery that is transformative of a particular discipline. So we need to have that kind of diversity in our research programs, and on the International Space Station we're able to do that because each partner functions independently in making their research choices and then chooses to collaborate as free entities. And I think that's a very important aspect of Space Station. To give you an example of that, we have a number of cardiovascular investigations going on ISS today. And those are very well coordinated in that there's certain data collected, such as Holter monitoring data, that needs to be shared by all of the partners across the same subjects. And those data sharing agreements are in place. And yet many different investigators from different countries are testing divergent and quite variable hypotheses about cardiovascular function, building from that common data set. So European investigators in CARD are looking at the cardiovascular system as a model of heart failure in humans at rest, whereas NASA is more interested in arrhythmias, more interested in the functioning of the heart in space. And the Canadian Space Agency is more interested in vascular pressure. So all of those are linked and related approaches. Japan is interested in Holter monitoring, but in a different way, and chose to implement their own Holter monitor instead of collaborating. And it's a strength of our partnership that those can be done within the umbrella of resources and balance and fairness that we have. Just to close off, I want to give you one other example where nations can very much differ in what they believe are the main objectives. And this is why it's so important not to have control, but to have collaboration. So in the area of protein crystal growth or macromolecular crystal growth, NASA chose to stand down in that particular discipline about 4 years ago. But other nations have chosen to go forward. And so, for example, JAXA has announced a number of breakthroughs where they've gotten important crystal structures from molecules that they've flown in space. They collaborate extensively with the Russians in that area. And I believe that kind of diversity allows us to get the most value, the most intellectual value, and the most scientific discovery from the space station. Thank you.
Thank you. Yes, please.
Я хотел бы обратить внимание на вот какой вопрос.
I would like to draw attention to the following subject. We have been talking about human health a lot, about countermeasures, about the impact on humans in space, but one very important element hasn't been mentioned, and that is the environment, the habitat environment in which the human is placed. For today, we have orbital flight, and we have already had cases on the ISS when the life support system had failures, but the ground was closed, and so they were fixed. But what is going to happen in autonomous flight? It's pretty clear that the lengthy isolation of human being in autonomous flight will indeed require involvement of biological component in the life support system. I don't think that we'll be able to have a full, to provide full nutrition to the crew during prolonged flight. Neither one dietologist was able to give me an answer to this question when the length of the period of study was posed before them. So we would have to use the human, the biological component. Most likely it's plants we're talking about. So what do we have to research today at the ISS? Yes, countermeasures indeed. Yes, health support. Yes, protection from radiation. But if we introduce biology and biological subjects and live subjects who are also exposed to stressful environment and biological effects, we have to study for today. Unfortunately, today, we do not pay enough attention to this very important issue. And without normal life support system, without normal inhabitable environment within a sealed module in space, no matter what countermeasures you take, chances are you reduce the chances of him coming.
I want to contribute a couple of sentences to this. Being a psychologist, I want to say that we're studying the new international research protocol related to the plants in space and in the chambers, and is based on the classic questionnaires approach, but also on the analysis of the positioning of the crew members in relation to the position of the greenhouse, which is extremely important. So we try to estimate objectively how much these objects are attractive, because we're speaking too much about the negative effects aboard, but it could be something that could be positive, like, for example, plants or flowers. It could be some other objects which could positively influence the human beings aboard, and I think this is a very new, interesting research area.
Other comments from members of the panel? Please.
I would like to continue what Dr. Robinson started about the organization of cooperation. I'm sure that cooperation should be organized, and the condition on which this cooperation, this organization should be based, they are obvious, and they were very nicely formulated in the talk which we heard today during our luncheon. And they are obvious, they are logic, no problem. But I was somehow influenced by Dr. Robinson saying that it is very important that those people who come to organize us scientists, they should have understand that their role is to help, but not to control, not to select the scientific problem, and even more, not to select the decision, how to resolve this problem, because those people who are organized in this cooperation, they are specialists, and they don't need ruling in this respect, in this direction. They need to be helped with some infrastructure, with some properly done agreements, and with proper supply, including foundation and so on. And that's what we are waiting from them. And that's why I have to say that I don't completely agree with Dennis Ground, who told absolutely proper that, yes, we do cooperate, but sometimes I would like to say that we cooperate not because of, but in spite of. We cooperate, or rather, I would say, we cooperate because of our interest, because this interest is common on both or three sides of those people who are flying, or who because of enthusiasm and belief and so on. But that's not proper for such venue like International Space Station and the future of the space flight. I think all of us feel like we address management. See, it is not very often that scientists address management. They ask management to help, for help in organization, to create the program, to support this program, to make the base for this program, and so on. Because, Dennis, you said absolutely properly that our cooperation with people from JSC, it is very strong, and I don't believe that something can put the end to this cooperation. This cooperation happened to start during Mir-NASA program. And we continue. But let me tell you, there is no one agreement about common, we use each other equipment, but there is no agreement under it. So actually I can be punished, or people on your side can be punished for giving us this equipment during pre-post studies, and even more on board. On board there is a lot of equipment, a lot of small ESA gas analyzer, which I tried to get to get access to it by different way. Like, okay, we are having nice experiment, countermeasure, evaluating of the in which we evaluate the efficacy of different exercise in weightlessness, and we invite ESA scientists to participate with us in this experiment, and it was very easy because we are close with the ESA scientists, because we were running together or flying together, the German and ESA astronaut Mr. Reiter. So we were doing together, we were like this, you know, but we never got permission for them to participate in our countermeasure experiment or for us to use this gas analyzer. So we're still running very important for everybody experiment on assessing the efficacy of different loading in space without proper gas analysis, which is actually not good. And this is just one example, but actually we have this, we don't have otherwise example. We don't have, I cannot say what equipment we were allowed to share, we were allowed to use, not speaking about making together some program of experiment. But I believe absolutely the same as what told today, that when you cooperate, it means that people from different sides have to work together. Not like I'm doing on my side this, some partner doing on this, but we don't have this, this even attempt to get together. And as I know that in spite of the fact that on USOS side, you have now all partners like their experiment are considered allowed and so on, but they're working by themselves and the other working by themselves. It's rather partnership than cooperation. Partnership and cooperation is different. So my suggestion, and I'm sure that we have to go this way. We have to and as a matter of fact, few things are already mentioned here, because it is said here about organizing of team of specialists, which will develop, the programs and which will work the strategy, the tactic, and so on, and we'll go this way. One thing, these programs speak about shared use of common resources. That's what I'm talking about. Now, you cannot imagine how much hardware, how much apparatus now we have on the station. But they're used like this. Because, like ISA, Cosmonaut 1 is flying, and he's doing certain amount of experiment, and all the other equipment is just spent there, I would say, yeah. So I think that somehow should be done, and the start should be done, and the structure should be created for organization this international cooperation and developing on of the strategy of doing the program, long-term program which addressed to the future, which will enlist all the question, all the problem which came from our experience from the future, and open the field for cooperation and for sharing data and resources and so on, rather than we will speak about it.
Thank you very much. Other comments from the panel, and then we're going to turn to the audience for some questions.
I would like to speak toward one future opportunity. The topic was brought up earlier about whether campaigns on the International Space Station would be a help or would not be as productive. And we've actually considered that there are at least a few campaigns that we can think of that would probably yield greater results than individual experiments trying to be combined post hoc. And one of them would be a campaign with respect to behavioral health and performance. And in that we would, and I think this would obviously need to be an internationally agreed cooperative campaign. But right now the experiments associated with neurological adaptation or sensory adaptation are not generally integrated with behavioral health experiments. And I think the model that you can hark back to is Neurolab, in which the experiments were both integrated scientifically as well as in their measurements. And I think that might make a nice campaign for the International Space Station. It would take some planning, and it would take some cooperation with respect to defining roles and responsibilities. But I think that's a place where we could gain some real traction.
Shall we take some questions from the audience at this point?
Question.
Please, back on the right side, and then we'll come back here. I don't know where the mic's... Oh, here, microphone is coming.
There's an old American cartoon joke that goes something like this: we have met the enemy, and it is us. And this is what this feels like to me. But I want to give you a perspective from a scientist's view who does work on all three of the venues you've seen today: ISS, NEMO, and the Russian Chamber. Here is the most remarkable thing. Do you know that in none of those venues do I know what the other science is? No one told me whether somebody else is doing something similar or different, the same tools, doubling the workload, causing a problem that would affect our data, and that is the single greatest barrier. I don't even know who these scientists are I'm supposed to collaborate with, let alone whether they've done something to screw up my experiment. And so what I would urge the managers who sit in their offices somewhere to think about is that if you want scientists to collaborate, do it the way it happened with our speaker today. She and her collaborator met at a scientific meeting, heard each other's presentations, discussed the common interest, and decided on a joint venture to discover the gene for a disease. Now, that's how you collaborate. That's how otherwise it's a forced marriage, and scientists don't take the forced marriages any better than young couples do in any area. Okay? If you want a courtship and a real love affair, you've got to tell us what the science is. We don't understand, by and large, why you think that has to be a secret. Why does it have to be a secret what the Russians or Europeans are doing in the chamber study for me? Or why does it have to be a secret what else is happening on ISS relative to me? Why can't I know? That would, by the way, that also helps the scientific integrity. These are quasi-experimental environments. They're not absolute experimental environments. I don't control all the independent variables, but for God's sakes, let me know what they are. It's like, imagine if I told you I run a laboratory, it's my lab, I study subjects, they're in the lab, but while I'm at this meeting, some stranger I don't know walked into the lab and did measurements and things to them. I would say, well, forget it. We're not having any of that. So if you want collaboration from scientists, instead of trying to talk about how to do it from a managerial standpoint, which is fine, tell us who the other scientists are and what they're doing, and allow us to interact with them.
Other comments from the panel?
I have a comment because I know what Dr. Dinges is talking about, actually. When one questionnaire was used 5 times, very close to each other, and it was real interference of data, and scientists didn't know each other. But I want to start with his first point about the cartoon, and we met the enemy, that were us. And do not forget what Julie Robinson told us 5 minutes ago. Some scientists are so selfish that when we propose, let us do something and share, they say, no, 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 no. Put him 5 polar watches and let him wear it for 500 days. Or give him to write 5 diaries a day and spread it. Will they be different or the same? 5 diaries a day. Could you imagine that? But we are scientists and we are selfish. Let us confirm, accept this, and agree on that. Yes.
The courtship has to be exposure at scientific meetings and scientific discourse. Trust has to be built up.
Sure. And I agree with the trust as the basic element of that chemistry, which was proclaimed an hour ago. But that chemistry should be based on let me offer you something, but you give me something also. For example, we heard about NEMO. Who participated in NEMO? Canada and US. What about Russians? Were they invited to participate into NEMO? No. Believe me, no. Same for another test bed called Concordia for European Space Agency. We are not invited. So we ourselves allow administration to create these barriers. And do not forget, that's us who are enemies. We are the first enemies of ourselves.
And one more thing. We are not, I don't know how much experience you have in international cooperation, but to my happiness or unhappiness, I have a lot. And one of the very best cooperation which I had, and I'm sure it should be given as a model, it is cooperation on our biosatellite, BION. This cooperation is example, and I'm sorry that actually we know, in spite of all our joint activity, we know so little about each other that I'm sure that among people here, just few people knows about this BION cooperation. But this cooperation gave exactly the proper model of cooperation, which completely is completely opposed to what you said. Every BION had the main theme, the main topic. That's it. Like, but I was the head of the primate program on vestibular and sensory motor. So there were 5 biosatellites in the row, and the priority was given to vestibular and sensory motor. And no manager would say what particular science should be performed. They say that it is necessary for our Buran flight. We need to have some data on vestibular and cognition and so on and so on. So the management applied to us, and we applied to the whole world. We said, we will have such and such condition. Who is interested? Apply. Then there was a proper concourse, scientific concourse. We were working together, creating actually excellent. I am proud that I was working with such people like Dr. Curry, best vestibular people in the United States. That was Korea, and that was Cohen. That was Reggie Edgerton. They were excellent people from your side. We didn't know each other before, but we were scientists. We made together program which we were flying for 6 flights, for 12 months. We got excellent results, and actually that is I think the model of cooperation which should be taken as a model for space research, because in space we cannot. I know your system of this free grant. Whatever we give you money and you have this concourse and you get something. In space we don't have so much money, as many questions we have to be successful. So some questions should be put, some money should be funded, and then scientific community should be asked who would like and who has strengths to participate in solving this question. And then later on, give them like or dislike together, group together, make this scientific group, and so on. So one doesn't contradict the other, Mike,
Let's take some more. There's another point from the panel.
Let me just quickly address a couple of points, because this is a problem that we discuss extensively on Space Station, and there are 2 things that we've done to try and address that. The first is that a year out, across the partnership, we maintain a common database which is posted for all the world on the World Wide Web, and it has contributions from every agency, from Russia, from JAXA, from ESA, from Canada, saying what the experiments are planned a year from now and who are the investigators. So it's there for anyone to search and anyone to identify if there's other research going on that they find of interest and they want to go seek those collaborations. The second thing that we're doing is we're identifying key scientific meetings in important disciplines that are international meetings to let our investigators know would be a focus of space station results in particular, so that those feed into the next round of proposals and the new research developed. A great example of this will be the Life in Space for Life in Earth meeting in Trieste is designated as one of those, hosted by ESA. And there's extensive Russian participation there. It's a great meeting to go to find collaborators with similar interests, and it's functioned that way for a number of years. Next year, Dennis is having all of his human research program investigators focus on humans in space, which will be hosted here in Houston for the same reason. So I think that those are really important ways to help those collaborations happen within the scientific community.
Thank you.
That's exactly proper way.
Let's take another question from the audience. Let's go back to Dr. Tour, then here, and then we'll come back.
Okay, I'm not here to criticize at all. I have enough trouble collaborating with people here on Earth. I can only imagine it's difficult in space. I've been serving, Neil has taught me to serve on government organization committees, and I've been serving for the last 18 months in the Department of Commerce's a stab at trying to rewrite export control laws and deemed export control laws. Deemed export control laws are what an American tells a foreign national within the U.S. It's know-how transfer and not material transfer other than source code. And then there are different laws when we go overseas, what we can tell people. And there's books on each of those. There's also laws with Department of Commerce and then with Department of State. And so each one of them has their books, and you're subject to violation on every standpoint. And the only reason why academics don't get caught so much, or don't because they just don't know any of this exists. But it is becoming more and more of a problem. We have just redrafted the laws, redrafted recommendations, and one of our recommendations is get rid of deemed export entirely. That's probably not going to happen, so we've come up with an algorithm that will cut out probably a good portion of what's in those books. But what I'd like to know is, first of all, are there any regulations that people in space collaborating between one nation and another are allowed to share and not share? Are there any laws that govern this type of thing? And also, can I help in this? So in other words, would you like me to bring something up and to say when there is collaboration in space, a recommendation is that there be no restrictions? Because one of the things that we've done is we've come with a very strong recommendation saying none of this should apply to universities. Because you can imagine in teaching, if you have a group of people you're allowed to share with and another group you're not. And in particular, there are different nations and what you're allowed to share with those nations. And two nations in particular that we're not easily allowed to share with are students from Russia and China. And I have 25 people in my research group. 24 of them are not Americans, and the vast majority are Russians and Chinese. In my group and in the United States, we benefit tremendously because of these students. We are the recipients of the good because of these students that are here. And so what would you like to see put in place? What recommendations would you like to see that space, once we go into space, that's out of the United States, that's off planet Earth, that there be no barriers to the exchange of information, so at least from a recommendation side, something like this can go forth?
Thank you. That's an invitation. Would any members of the panel have a view on this matter of U.S. export controls?
I'll just say something. This is an area that actually really hurts us. And the one I've used is the UN Treaty on Outer Space that was signed in the late 60s, of which the U.S. and most of the spacefaring nations, or those interested in it, have signatures on. And it basically says that if you identify a hazard to health, human health in space, you're obligated to share that across nations. So when I get tasked or challenged as to why I'm talking to Dr. Chen or some of my Russian colleagues about something, I will say, well, I'm under the UN Treaty for Space, and I've got it on my computer, the actual law, but that's the one I think that we can use for specifically for sharing information about space health effects. And I think that it was signed long enough ago, and it's a treaty that it probably could at least be used to preempt or override some of the export control laws that have been signed subsequently.
Any other comments from the panel on this issue? I mean, this export control thing has driven me absolutely nuts. George Abbey and I have written on this subject, lobbied on behalf of this issue. The United States has not been in a good position on this matter of export controls, and as you know, has gone back and forth through the years in defining space technology and space issues, either as an item to be handled by the Commerce Department or, as it is currently now, handled by the State Department. And both are large bureaucracies and the huge amount of uncertainty associated with what might be approved, when it might be approved, might it ever be considered, and so forth. We recognize it's done enormous damage to international cooperation, not just in space, but in science, technology, in other areas as well, and it's damaged seriously U.S. industry in many of these quarters. So it's a serious problem. We are now coming out of a relatively long period in which this country was viewed as being less than, I would say, collaborative on issues of technology, and certainly space. We are all hopeful we're moving into a different era in which the things that we're talking together about here will come to pass, and the United States will remain an important partner in these activities in the most positive sense of partner. Sorry about that, but I had to get that off my chest. So, a question over in the back. Yes,
okay.
Man with the mic. Sorry.
Thank you, Neil. I would like to ask the panel and others in planning their experiments to distinguish between just getting to Mars and when going to a place like Mars is, well, I can't say more routine, because it'd probably never be more routine, but it could be more commonplace. I get the impression that most of what you're addressing has to do with those things, like having some flowers on board to improve the psychology. I don't know of any frontier that's ever been broken with any kind of luxury involved in it. I mean, you're going to pay a price when you're breaking a frontier, and I'd like to see us not be held up to go to Mars because it's something that'd be nice to have later. And you should take into account the value of qualifications, training, motivation, things like that, to overcome many of these things, which I think are, quote, nice to have, but you can do it the first time without it.
Comments, please.
Я бы
I would like to remind you that any organism, and not just human organism, in microgravity, in weightlessness conditions, experiences stress, and we have to do things so that this organism is viable there. This is not simple. A flower is not going to grow just by itself. You can't learn how to do it in 2 years. And therefore, the real issue here is not psychological support, but provision of a full, complete components for the tissues that are necessary, the full nutrition. And nutrition, the full complex of nutrients can be obtained from plant food. And in order to obtain the gamut of those nutrients from plant food, you have to learn which plants and how to grow them. We already can do that. But in order to feed 6 people, 6 crew, with daily dose of vitamin C, you need a hothouse of about 10 square meters. area. And this technically may be a little complex. In addition to that, there is a huge issue, and Canadian Space Agency in particular, in the US are focusing on that. What if there's a different kind of pressure on board? You have to take that factor into consideration. You have to learn how to grow plants in the environment with different environmental pressure. And so these are issues that are in part solvable on the ground, but we cannot imitate weightlessness on the ground, because the weightlessness is not only the absence of gravity, it's the alteration of the physics of the environment. And it's such an alteration that has a radical effect on the organism. And if it's a human being, his motion is in such way that the convection flow is created differently, and so there's no convection flow in the weightlessness conditions, and plants require the same thing as well. And if you are talking about plants drawing water out of the soil, and if you think then of weightlessness, how is that going to happen? So this is a separate, huge subject. It's not a subject of luxury, it's a subject of survival.
We should not deliver to Mars just muscles and bones. We should deliver there the capable, healthy, and motivated subject who will be ready to make that greenhouse not only aboard the spaceship, but on the station, to live in there and to do some practical job, to be mentally in good shape, to the person who physically perfect, because he has to work in the spacesuit on the surface of another planet. So it's a complex of problems, and we should not divide them into muscle and bones, into psychology. The complex approach needs cooperation. That's actually why we need cooperation, because each of us, for example, can study one question for his whole life and put an end at the end of life, put the dot. But it's the complex question. There are so many factors influencing that we cannot concentrate, for example, only on microgravity. This is not enough, and this is not a proper approach. So again, if we come back to what Chaki Mukai told us in the morning, this is more general fundamental problems where in which mankind is interested. Why to go there to Mars? Not just to put there the banner. No, we have to come there and work there and try to analyze how different nations could interact there. We cannot interact here on Earth properly. And space from that point is a test bed for the elaboration of that kind of cooperation. We collaborate better in space than on Earth. So, yeah, from that point, again, I think that flowers is the key issue, if you understand what I mean.
And Walt, I'll keep my comments brief, but I think if what you're asking is, can we reduce the hardship of a 3-year trip to Mars, accept? I think you said, should we be preparing the people to accept more hardship? I'm afraid we're going to get some hardship no matter what we do. Currently, out of the hundreds of foods that are qualified to fly for the shelf lives that we have for a shuttle and station, I think there are only 7 that currently meet a 3-year trip to Mars. And the dialogue between long-duration flyers and short-duration flyers with respect to the aspects of their environment and their food has changed a lot. Yeah, well, that's true, and I know you enjoyed your 4-day trip, but this is different.
Let's take another question from the panel.
I just want to follow up on that. You mentioned how important it was to understand the psychosocial, cultural factors for crew collaboration and mission success. This morning we heard how important it was to share the findings from Space for Health on Earth, and considering we need that political and public support and that half the population on Earth are women, why are there no women in this experiment, and do you think that will have any impact on crew selection for Mars?
It's a usual question, and let me give you a very short answer. I think we're always full of prejudices, and prejudices are based on one particular result. And the particular result of the previous study in 1999 was based on the conflict with participation of women aboard. This is a very wrong conclusion as for me, but that's how we decide in our normal life. Not scientifically, but on trying to avoid mistakes as much as possible. I think this is a mistake in general, but it's embedded, and we have the all-man crew. But believe me, if you think that we could have all-women crew, that could be the next, for example, study, and that will be a pure study with comparison with the previous one. So it's not only a disadvantage, it could be regarded as an advantage. Next time it will be all-women crew. Could you imagine that?
Why to have all-women crew when we have now flying mixed crew and we have women almost in every crew and everything is okay? And women doing not worse than men, not at all. Nobody told us that they were worse in anything, you know. And even nobody told us that the crew mixed was in any respect more inconvenient or more, less effective than just one gender crew. I think that in a way it is your error, Radim.
I agree. I agree fully with you. Women are always right, and that's for sure.
Other questions?
I just wanted to make a general comment about collaboration and knowing what your neighbors are working on and not knowing, and how that can be a problem sometimes. Someone of my generation is very used to social networking, and I think that would be a very useful tool because everyone can post to everyone else updates, everyone can have their own page, and it becomes a very passive activity to know what everyone else is working on over time. And you just gain a general knowledge without having to actively seek out information.
Thank you. Other questions or comments?
I'd like to clarify this Dr. Dinges' comment, and since I implement Dr. Dinges' science, it would be probably appropriate. I'm glad that Julie mentioned that ISS science is available. I spent several years in ISS payloads some time ago. But also, the availability of information about science depends on the contractual issues. Don't forget, we're not in the marriage or courtship. We're in the prenuptial stage of it sometimes. And when the contracts are not signed, that science is not available. Like Mars 500, for example, is a good example of it. Right now, Mars 500 science is available on the IBMP website, but it's also summaries. So technically, we can check it. So it's not quite that we don't know about this. But the other availability also should be pre-discussed, so to speak, when you enter any project. So it's another side of it.
One back at the back.
So I think the part of the issue here is trying to sort out really 4 different boxes here. One is the one-on-one scientific collaboration. I have 7 of those in my lab, okay? There was Singapore, Australia, Stanford, Harvard, okay? Those are fairly easy, fairly common among scientists, and that's what we heard at lunchtime. We heard a one-on-one collaboration. But a lot of what we're talking about is a one-on-many, or one with many. Or one person does the actigraphy and shares it with many, and that we don't have a lot of models for that. We're looking for models. The genetics area has it now, where you have to have whole teams working on projects. But I think that's one issue: is just how do we pool our data, our knowledge, or share data, so that we don't ask participants in studies to do the same thing 5 times, as one of you said, and avoid that problem. And then those 2 areas break down into knowledge of or awareness of, without necessarily an active collaboration, and versus an active collaboration where you're actually meeting to discuss the science. And there's probably Some of them are more achievable out of that 2x2 matrix. Some things are more achievable than others, but all 4 of those could potentially go on to varying degrees depending on what opportunities are created internationally. And it really begins with some sort of an international understanding to go ahead and reach out or share or cooperate.
So I would say that
Any comments from the panel?
Well, I think it's a good point. I think it's we are not talking about just personal chemistry between 2 people that exists, but we need a system. And that system, by the way, existed within the frame of European Space Agency. In the 90s, they had, for example, international group of psychological experts who were determining the trends for the future development, which areas of research are more perspective. They also formed the board for the selection of the experiments in space and in space simulations. I think if we can work on this, we could have the joint research protocols aboard. And that's the major, I think, area of interest, because the statistics based only on Russians or only on Americans, it's not good enough. At the same time, we can contribute with our approaches, with ideas, and not just share the data, but share logistics, share methods. And this is the only way for the future. Or, again, the crew member will do the same test 5 times.
Please.
So the high-energy physics community is perhaps a good example of a place to look at how you set up a large international collaboration to solve a problem. When decisions are made, for example, about what's the challenge, what's the next physics frontier that has to be addressed, the community gets together and it sits down and it decides we need to build a machine that goes to this energy to solve this problem. We can only afford to build one of them. We decide we'll build it in Switzerland. And a number of groups form to decide what detectors need to be built, and they build 5 or 6 of them that are positioned at critical points in the accelerator to solve very particular problems. And you have teams of hundreds of people working from many countries to address those problems. And in a way, your mention of the genetics community's approach to some major disease studies actually builds on the way the physics community has done it for as long as I can remember. So maybe what we need to do is invite some of those people next year to see if they can help us figure out how to set up these multinational teams to approach fundamental problems in science. So that's one. And I'd like to give another example from my own experience, that necessity and delays and scientists together not force, but unwittingly lead to the sharing of information. Working 24-hour clocks at an accelerator with delays and people doing all different kinds of experiments. You'd be amazed at what kind of scientific dialogues happened over coffee at 3 o'clock in the morning that led to new collaborations. And just putting people in a room and leaving them the opportunity to sit and talk about what they're interested in goes a long way. And the more those opportunities can happen, and maybe even with a little extra stress thrown in, sometimes really good things come out of that.
Then could you pass the mic down here? Let me just mention what I think you all know, that Dr. Sam Ting will be here tomorrow, I believe, right, unless, is he going to be here? Oh, I'm sorry, okay, I see. Well, let me just mention, though, that he, of course, is the person running the AMS experiment, so he's a person who has experience in the high-energy physics community in precisely the way that was just described, but also for a long time now he's lived with a somewhat different experimental environment in which you have to do things, you have to worry about things that he didn't previously have to worry about. So he would be a good person to have a discussion with.
I want to second Dr. Cronenberg's comment, because I was part of one of those crews working 24 hours in a particle accelerator. It's quite similar to spaceflight mission in some way in terms of stress and psychological factors and human factors too. But I think what she mentioned at the beginning about this physics community, a good example is the RIKEN project. So Japanese, American, and other international partners that for many years have collaborated not only in physics but in other areas of life sciences. And a good example of these international partnerships and collaborations. So I suggest for next meeting, maybe some representative of the project will be very helpful.
Thank you. So there's some, here's a mic back here, and then let's pass this
now that we're back on the
up.
collaboration topic, I'd like to make a comment. In a personal experience, at some point years ago, I was involved with a space psychology group that was run by ESA. And they invited me because the times were such that they were trying to expand. Then NASA Mir came along, and there was a decree for Americans and Russians to find collaborators. For me, it was easy. I knew Dr. Gushin, I met Dr. Solnitsky, and I've had, I think, from my viewpoint, a wonderful collaboration with the IBMP. Then ISS came along. The ISS, the Mir disappeared, but we managed to find a way of finessing through subcontracting mechanisms the continuation of our relationship. And then we went through a period where of the export law, and Congress didn't want to do Mars studies, and we want to go it alone. And I was clamped down. And I'm sure I'm kind of the bad guy for some people now at the IBMP because I couldn't collaborate with them. And now maybe things are loosening up. My point is, over the years, these things come and they go. I don't think the problem is the scientists not wanting to collaborate. I think the problem has to do with larger issues that affect the agencies politically. And I think it's kind of up to the agencies to figure out some way of lobbying, even perhaps against their own administration, to allow this kind of collaboration to occur. I mean, you have to be kind of stupid not to want to collaborate now because you get a lot of subjects if you look cross-culturally. Otherwise, you have 1 or 2 subjects a mission, and you lose the end, you lose power. And the fact of studying 6 people on a mission is wonderful. I think most of us would love to do it and would love to collaborate. So I think the issue isn't so much the science at the science level. It's maybe even beyond the agency level. But all of you, I hope, can perhaps find a way of lobbying and collaborating yourselves so that we can break the barriers that allow us folk to meet our peers, to interact with them, and to do good science.
On the topic of getting to know the other investigators on ISS and these other analog environments, probably about a third of the people in this room are veterans of the Space Lab era. And I think many of us who worked as investigators on those flights fondly remember having to travel to investigator working groups. And I believe that that's where we really got to know one another. We had to work out all these compromises. Those missions took a couple of years to develop. It was an expensive process, and I recall in the early days of Station on the SAS, Don, you can back me up on this, I think, we had some discussions about whether we should continue to have investigator working groups. And I think the scientists on the SAS pushed for it, but many others pushed back and said, no, we can't afford to do that. There are too many people involved. There will be too many people involved. We can't really you might get assigned to one investigator working group, but your experiment might be delayed an increment or 2 and you'd get to know the wrong people. So there were a lot of arguments against it. Yet I submit that these IWGs were really important for the culture of Space Lab and for team building and getting all of us on the same page in terms of setting goals for the mission. The focus was on the mission and not the process. And perhaps at least if we're going to think about dedicated increments, discipline-specific increments, maybe we should be reviving the investigator working group concept for those flights.
I think I would like to give some the perspective about the issue about this issue as a kind of the follow-up that Nick Canis mentioned. I think the success story that we have learned from the lunchtime was the so-called active collaboration. So the PIs or scientists feels like by collaboration, both sides or amongst the scientists feels like we are benefited. And then the other ISS or other issue was a kind of passive or artificial collaboration, like usually the agency, because of the resources, because of the political issues, or because of the money or something like that, try to make some group of the scientists to make them work together. But it does not necessarily mean that each of the scientists feels like we are pretty much benefited by this collaboration. It's more artificial or given or passive collaboration. That's, I think, the why. I think some of the PIs or scientists don't feel like it's a good way to do it. So my suggestion is maybe the agencies or some kind of organizer needs to find out the mechanisms to matchmaking the scientists who really feels like the collaboration makes them benefited, maybe psychologically too. That's my suggestion.
Please.
Thank you. I wanted to talk about a little different subject, and that's the Institutional Review Board process, as it's called at most universities, or what we started and what Dr. Dahman is a current member of for ISS, which is called the Human Research Multilateral Review Board. The reason I want to bring that up is Dr. Dinges was concerned about whether there'd be conflicts by other experiments on his particular mission or study. And although we may not have always done it well, one of the things that we did is we looked at the mission as it came together, each mission or increment, if you like, on station. And we looked at simple things like blood volume requirements to make sure we weren't depleting the total blood mass. But we looked at more subtle things like what at least 20 members from different disciplines thought might be potential interferences among the experiments. So that's always been considered and is today as far as I know. So it may not be perfect, but it's part of the process for trying to make sure that an individual investigator gets the best results he or she can.
I think what we're hearing is the appeal for integration, scientific integration by design that is ahead of the mission. That's what Chiaki was talking about. That's what Dr. Ullman was talking about. And I think the situation that we're running into or have run into that Dr. Dinges was talking about is the post hoc integration after the objectives are all put together, and now you're looking for conflicts, you're looking for overlaps. You're be lucky if you found some synergy or efficiency, but mostly you're looking at practicing defensive science at this point in time. And I think that's what he's suggesting we try to avoid by the proactive planning that looks at the integration and the possible efficiencies ahead of time, which we all know how to do from investigator working group, but the large, complex, and continuously operated vehicles are a more difficult problem than discrete missions.
I don't think we need, speaking about the modern types of communication, we do not need to come to one room and discuss every day the same issue. I think using modern facilities, these groups could work their own institutions. So it's not mainly about funding. It's about the intention of the scientists to cooperate, as Chiaki is saying. And if agency will support those who are really prone to cooperation, that will be the support not only for the better research, but that will be the support for the scientific school. Because when I have to work together with the leaders international leaders, I have to improve myself. So that is how to make the level of science, state of art in psychology, for example, higher from that point of view. And second issue should be the international, let's say, research platforms. Because by international, I mean not two countries like Russia and Belarus, like US and Canada. International means that all agencies like ONSS can work and make their joint research protocols. Could be like polar winter in Concordia could be like IBMP complex of chambers, which is unique, and it's not necessary for any country to build the same. It could be NEMO, because NEMO is also unique. But if it's international, we can make each day of experiment there more full of scientific, meaningful research. What we're doing now, we're just trying to reproduce something made in US, in Russia, then that will be reproduced somewhere in China, and we're not moving forward. We're just reproducing each other, and we're all satisfied because we have very good national programs at the end, and we are very satisfied people.
Julie?
I'd like to address a little bit more from what Dennis said about the Space Lab model compared to what we have with a continuous program. So, you know, in the Space Lab model, a team of scientists was working together for 2 to 3 years at the least to plan a 2-week mission. And they were divvying up a very small number of resources with relatively centralized control over what the priorities were. On the space station, of course, we have investigators in and out every day of the week. We have about 130 active investigations at any one time, and those roll over at a rate of approximately every 12 months. So we're seeing roughly 200 investigations rolling through in 2010, for example. And we have at the beginning of each 6-month planning period, we have something called an investigator symposium. It has 2 purposes. The first purpose is to make sure that the scientists who will be doing that day-to-day management have at least at one time, with that many investigators out there, at least once heard from those PIs about their objectives and what their thinking was behind their requirements. And a secondary objective, and this has been particularly important to ESA, who has insisted on the development of the process I'm talking about, we group the investigators that are working on common disciplines together. We find that many of our investigators don't want to participate in this particular symposium, and I think you're probably aware of that, have experienced that yourself with your investigation. And the reason they don't participate is because they already have the resources assigned and the protocols approved, so they don't actually care to collaborate at that point in time. So it's definitely not just about the agencies. It's also about the investigators' perceptions of where the decisions will be made about their experiments. They participated in Space Lab because if they didn't, they weren't going to get their cut of the time and the resources to do what they wanted to do. Once they think they've got that cut, they really want to go ahead and do what their initial intention was, and they're open to collaboration as long as it doesn't get them off track. So it's definitely a challenging problem with a continuous vehicle.
We have time for 2 one in the back and then one here. So please, in the back.
I have a very small comment to make. Probably an easy way to give a little help for an international collaboration since starting, it would be to have a possibility to get funding from the same agency for the whole international partnership, which is now completely impossible. I mean, every time you make up, you have a question, the question has to be addressed by specialists by several countries. Each one of that specialists have to get money from his own agency. Now that is something which slows down the process since the beginning. And that might help to find a way that instead this kind of limitation would not be true.
Thank you. Please.
Yeah, some follow-ups to the Chiaki's comment about the active participation and Dr. Sorin's the comment on the HRMRB, the big IRB. As a practice, they trained as the clinician. I'm trained not to watch the way from the reality, and there was no mention about the Space Lab model, but I hear that there were so many conflicts, and they had some bloody duels conducted behind the scenes, and so much frustration from Dr. Yang and Dr. Omar, and why those are not well integrated. And from the HRMRB view, I can share that because I was associated also before the IRB was formed. So seeing from the IRB, why not these integrated is the question. But I saw some not pleasant meetings like at ESA, ESA had a very integrated, long-range plan for neurology research. So they assembled some scientists at the place and had a discussion. But what I observed was that among the scientists who doesn't know each other, there are so much suspicions, and are they stealing my protocol, that kind of a thing? So the in the space lab, magically it was integrated, but unless they know each other well, it doesn't work as the IRB desires, is what I have observed in the years.
Thank you very much. We're at the end of our session. There's no way I can summarize the richness of what's come from the panel and from the audience, except to say we're all in the room in favor of collaboration. It's extremely difficult, and all the partners have to share in the results. There are some issues that we've started to discuss. I think funding is a major one for this country because I don't think it's really been addressed yet. I don't think the public has focused, American public has focused on the implications of future space travel. So we have a lot of work to do, and we expect to get good guidance from all of you. Please thank our panel. I invite George Abbey back to the mic.
Thank you for keeping this discussion going.
That fella, good. No, there is no break. We're going to have a break in just a few minutes, but there's no break now, so everybody should hang in there. Take your seats, please.
If you all would take your seats, please. We're going to continue with the program.
That's all.
Hmm? What does he have to do?
It's no, it's black. The first screen is black.
Hmm?
The first screen is black.
That's it.
It's there, but it's not here.
What do you want to do? Use this?
Yes, this is the remote. Yes, I just want to make sure it's on the screen.
So you just have to push this?
Yes.
Our next speaker is Dr. Gene Levy. Dr. Levy is the provost of Rice University. He's been the provost for the last 10 years and will be retiring as provost this July. And then he's going to take a year sabbatical, and then we're very fortunate to have him joining us here at the Baker Institute as a senior fellow in science and space and education. So he'll be here at the Institute, and it's going to be great having him here. He is also going to be a professor in the Department of Physics and Astronomy. So let me introduce Dr. Levy. He is really, his leadership and vision that has given us the Bioscience Research Collaborative, and he's going to talk to you about this afternoon. Gene, just press that.
Sorry?
I'm having trouble getting on this screen.
It's on that screen or this screen?
This screen.
Don't worry about that. Okay. So, good afternoon. It's a pleasure to talk with you. I'm going to spend a few minutes telling you about the Biosciences Research Collaborative, about the motivation for it. I'm not going to go into some of the detail about the current program because when you go over to the BRC, Cindy Farah-Carson, who is our Associate Vice Provost for Research and who has a major responsibility in implementing the Bioscience Research Collaborative, will talk to you more about the current program. What I thought that I would do is give you a little background, not an enormous amount, but just a sense of context for this project. It's a context that began to come into shape about 8.5 years ago. The Biosciences Research Collaborative opened about a year ago, about 10 months ago actually. Something that's very gratifying for us, and a facility and a concept for us that is intended to substantially increase the intensity of the relationship between Rice University and the research institutions and educational institutions of the Texas Medical Center. So I'm not going to be very complete. I'm not going to spend a lot of time talking about the current programs. Dr. Farah-Carson will talk about those with you when you go over there for the tour. But I will give you some semblance of the motivation in the background. I just pushed the button and nothing happened. The motive behind the establishment of the Biosciences Research Collaborative starts conceptually. And it starts with a set of premises about the progress of 21st century biomedical science. And in particular, that a number of premises. One, of course, I think that is unarguable, is that biomedical science, the research behind it, is already playing a role in the 21st century that perhaps is analogous to the role played by electronics and computation and communication in the 20th century, meaning not only is it going to be one of the great motive forces behind the advance of human capability and human welfare, but also one of the great machineries, one of the great engines of economic progress. A lot of this change, I think, is clear as a result of the fact that biology itself and biomedical science has made the transition in the 20th century from a largely empirical and to some extent until the latter part of the 20th century, somewhat blindly empirical pursuit, to a pursuit that is based increasingly on a mechanistic, from a machine point of view, a mechanistic and physical understanding of biological systems, both in their normal states and in their pathological or disease-disrupted states. I think it's a very, very important development intellectually in terms of human capabilities for improving life. As a consequence of that, progress and leadership in these developments in biomedical science depends increasingly on the very close interplay between the traditional areas of modern biomedical science and other areas of biology, as well as physical science, nanotechnology, engineering, computation. We could go on and on. But one of the remarkable developments in the 20th century is the degree to which medicine has become a hand-in-glove activity with physics and chemistry and computation and engineering. And that's an extraordinary development. And in the last decades of the 20th century, and increasingly as we move into the 21st century, medicine has become increasingly linked with nanoscience and nanotechnology, which is a word that means really nothing more than the ability to manipulate the structures and functions of systems at the molecular level in a rational way for rationally designed purposes. Something, of course, that is critical for the development of biology and biomedicine. In the 21st century, science and technology are driven increasingly at all levels by this rapidly growing ability to manipulate matter at the molecular level in a deliberate and targeted way based on an intimate knowledge of the relationship between structure and function of matter at the molecular level. And this also is going to have, and is already having, a profound impact on the progress of medical science, as well as the progress of material science and science in a whole host of areas. One of our challenges is to make use of the capabilities that exist throughout our regional environment, to bring together those capabilities to grow this science as rapidly and as deliberately as possible. At the same time, while I've talked a little bit about, or I've mentioned a little bit, the impact of the increasing our knowledge of the relationship between structure and function in chemical systems, molecular systems, the impact of that on biology and biomedicine, we shouldn't forget that the feedback goes in the other direction, and increasingly our research and development of processes in chemistry, for example, depends and makes use of ideas and techniques developed from biology. I'll just very briefly give several examples, and I'm not, as I said, trying to be current in terms of the research programs at the Biomedical Research, Bioscience Research Center, but just some motivational examples. So, for example, one of the approaches to cancer therapeutic developed as a collaboration between electrical engineers, physicists, and cancer researchers here between Rice University and the Texas Medical Center over the past decade involves the deployment of nanoscopic shells of gold plated on silicon cores that are tuned to absorb light very effectively at certain frequencies. And these shells can be decorated with ligands that target cancer receptors on cancer cells injected into the bloodstream, attached to the cancer cells, and then illuminated from the outside with red laser light that penetrates tissue, but that is absorbed preferentially by these shells to the extent that the shells heat up and destroy the cancer. This is a technique that's currently in trials at the Texas Medical Center, making use of advances in electrical engineering and physics, in plasmonic physics, and in cancer biology. The kind of cross-disciplinary symbiosis in biomedicine that really promises extraordinary things for the future. Similarly, we have programs that combine photonics engineering with to guide surgical techniques, surgical procedures in the midst of surgery, for example, to find the boundaries of cancers during surgery. Vascular and other kinds of tissue engineering, I just put this one up as an example because I had the slide. At this point, there are far more advanced levels of tissue engineering that are currently under research around here. As I've said, something that you all know, of course, that the ability to develop drugs is becoming more and more rational, and combining the deepest kinds of chemical and molecular science and applying them to the treatment of disease. This is an example of the drug Gleevec. It shows how I don't have a pointer. Maybe I do have a pointer. But I don't know what that did. Oh, here's the pointer. Doesn't show up. It's showing how the red embedded Gleevec molecule interferes with the metabolism of a leukemia pathway. Again, a rationally designed, computationally rationally designed therapeutic. we're looking at the creation of new classes of hybrid biological and physical devices. I'm sure this is like carrying coals to Newcastle. All of you know this at least as well, probably better than I do. But combining the expertise found in, for example, electrical engineering departments with the expertise in neuroscience programs to develop hybrid neural electrical devices for ultimately to find their way into therapeutic application in medicine. And similarly, the development of sensors and transducers to be able to sense the chemical environment in the body for diagnostic purposes. All of these kinds of activities require a breadth of engagement across the areas of physics and chemistry and engineering and medicine in ways that 30 or 40 years ago were only primitive and not used in any way to the extent that they are today. Lastly, I'd mention that of course, as I've already suggested, the value goes in both directions. Not only are the capabilities and knowledge in the basic physical sciences and mathematical sciences informing biology and biomedicine, but the informing goes in both directions as chemistry increasingly makes use of biologically inspired processes for chemical synthesis. I mean, so what we have been looking at here, and I'll put up this diagram just to be suggestive, because it is suggestive of what we're trying to achieve on the ground. That modern biomedicine exists not so much anymore as a discipline unto itself, but as a discipline that exists at the nexus, at the center of traditional physical sciences, engineering, computation, as well as biology, and that overlap, that Venn diagram overlap in the center, is going to be, I think, and it already is showing itself to be, one of the most exciting areas for not only increasing our knowledge of basic science, but increasing our applications ability to improve human life through therapeutics and other means. And one of our challenges is to try to build the greatest strength of opportunity that we have at the center, at that intersection that we currently can. To some extent, we in Houston have worked at a disadvantage, competitive disadvantage, and a disadvantage intellectually, because of the absence of integrated institutions that combine and co-locate in the same institution the capabilities of not only of medical schools, but of physics departments and chemistry departments and mathematics departments, because Texas has chosen as a state, unlike many other areas, to separate the medical schools from the universities. And so here in Houston, we have an extraordinarily strong university that we sit on the campus of right now, Rice University. And across the street, we have the extraordinarily strong concentration of research in biomedical areas, a wide variety of biomedical areas, ranging from basic research important to biomedicine to the clinic. But we do not have in the same institution all of these combined areas of focus, all working together. So our challenge then in confronting the future has been how to capture the value that Houston has to offer if we could bring our capabilities together. We have here, and I'll show you in a second in the diagram, within about a half a mile of where we are sitting, and one of the world's greatest concentrations of biomedical research, and we are sitting on a campus that is one of the nation's leading research institutions in the physical sciences, mathematical sciences, and engineering. Yet having been separated not only by Main Street, but by institutional boundaries. And our challenge has been how to bring those together. This merely repeats what I just said, so I won't go through this. I will note that the institutions involved include the Baylor College of Medicine, the MD Anderson Cancer Center, University of Texas Health Science Center, the Methodist Hospital, the Children's Hospital, and Rice University, among others. What this diagram shows is the relationship amongst those. The The greenish area is the Rice University campus. If I had a pointer that worked, I would. Oh, there it is. I don't know if can you see that? No, I can. We are sitting right there. If you can see it in the Baker Institute. What I have drawn. This is a diagram that I drew a number of years ago. It is a 2,000-foot, or roughly 600-meter radius circle centered on a piece of land at the intersection of Main Street and University Boulevard. The greenish area is the Rice University campus. The orange area is the Texas Medical Center, which shows within a 2,000-foot or 600-meter radius circle much of the Rice University campus, the Baylor College of Medicine, the MD Anderson Cancer Center, the Texas Children's Hospital, the University of Texas Health Science Center, and the Methodist Hospital. An extraordinary opportunity for us. What we decided to do a number of years ago is to take advantage of this strategically located piece of land that I've shown now in a light-colored green. It's a piece of land that Rice University owned. Used to be a hotel that you could rent rooms in by the hour. Then it was upgraded to a graduate residence hall. And there are no implications there. But in any case, it is a piece of land that Rice University owns. And this diagram is intended to point out the strategic value of that location. And the use that it could be put to that would be even higher use than a by-the-hour hotel. So we sought to develop that land into something of much greater value. What is of much greater value on it now is the facility that you will tour this afternoon, the Biosciences Research Collaborative. The Biosciences Research Collaborative opened about a year ago, about 10 months ago actually, in the summer of 2009. It is a 480,000 square foot facility, about 45,000 square meters of research space, consisting of laboratories, offices, and interaction areas that you will tour. It is, as I've already pointed out, it's strategically located. Not only is it so close to all of these research institutions and the Rice campus, but not far from this location is the University of Houston, a couple of miles to the east, and somewhat farther to the south, the University of Texas Medical Branch at Galveston. So a very, very rich research region, not only rich in the basic sciences, but extraordinarily rich in the biomedical sciences and the clinical sciences, providing us a research environment that is not exceeded by any other research environment in the world in terms of its capability. Our goal is to make the best possible use of that research environment. The Biosciences Research Collaborative is situated at this intersection of the Rice campus, which is to the upper right, and the Texas Medical Center, which is below, a little bit to the left of this region, and it's designed to have easy access to all of these institutions and to be a magnet, a kind of a hub, bringing researchers together for collaborative research, not just collaborative research in biomedicine, but collaborative research that engages, as I have said, physics and chemistry and engineering and computation and mathematics with the biomedical research and the clinical research of the Texas Medical Center institutions. Just very briefly, this is what the typical floor plate of the Biosciences Research Collaborative looks like. The yellow at the bottom is laboratories, then offices, and the round area is interaction regions, interaction sections, both to house graduate students and to and seminar rooms and coffee rooms to provoke interdisciplinary interaction, to bring people together. In the whole building is designed to try to bring people together and provoke effective collaborations across the broad disciplines intended to be housed there over time. Over time, the building is expandable to a second stage. The second stage is shown at the top, and we are looking forward to saturating the first stage with use and being forced to build the second stage of this building in the not-too-distant future, we hope. So just to close and summarize, I will mention that, of course, we continue to confront broader challenges. Building a building and creating a venue is a very, very important step. Organizations have an extraordinary ability to be self-protective, since we're all in this room in one level or another interested in biological systems and their so the biomedical implications of biological systems. If you think from an evolutionary point of view in the origin of life, one of the first things that an organism has to accomplish is to develop systems that distinguish itself from the environment, distinguish itself from other. All biological systems do that. Unfortunately, academic institutions and academic departments are very effective at distinguishing themselves from others as well, and building barriers, membranes that separate their processes. And one of our challenges is to penetrate those membranes and to penetrate the membranes that distinguish self from other, and create greater senses of self across institutional boundaries. And so we're working on that, and this is a work in progress. I think I will stop there and invite you all to take the tour of the Biosciences Research Collaborative that's on the agenda for the last part of this afternoon. I think you will find it an exciting venue, and I hope that we'll see some of you, or maybe more than a few of you, working there as visitors in the future, as the NSBRI is intending to locate its next facility there as well. So thank you very much for listening. Of course. Yes.
So your last slide made a pretty strong statement for breaking down barriers and linking institutions together. I know Rice explored at one point actually a merger or acquisition or whatever with Baylor College of Medicine. That obviously must not have been an approach that seemed feasible or productive. Can you tell us, are you continuing to explore things that would go beyond simple collaboration with academic medical center?
So let me say, I think there remain possibilities on the table. We are not, at the present time, engaging in that conversation. We engaged in that conversation for a period of time. It was a very exciting conversation. In the end, we concluded that it was not an opportune time for a number of reasons. That doesn't mean that it will not be an opportune time for all time in the future. And I would not be surprised if this subject were to come up again at some other time in the future. But it's not a conversation that is currently ongoing. Yes.
Yeah, is the research center completely funded by Rice, or are there other funding sources?
I'm sorry, excuse me?
Is the center funded completely by Rice, or are there other funding
sources? Yeah, the BRC was funded entirely by Rice. We are expecting Texas Children's Hospital. They've already made a commitment to move research programs in. So the way that works is that they will, and others that move in, will bear the cost of building out the interior part that they use to their needs, and then pay a rental for the use of space and for the sharing of the common areas over time.
Is there any cooperation or, I guess, coordination of the types of research groups that are being invited?
Well, we're only interested in hosting research collaborations that are mutually beneficial and advanced programs of both participants. And so the door is not open to just anything. The door is only open to research that makes use of the complementary capabilities of the occupants in the building. Now, one of the things that one of the motivations is, I think, should be clear, is that we are, not insisting, and I think it would be hugely counterproductive to insist that we only were hosting research projects that were previously defined. What we are doing is seeking to put the right kinds of people and the right kinds of social dynamic, intellectual dynamic in the building, so that the collaboration and the new ideas will ferment and be developed. It's not a question of just trying to bring in collaborative projects. We're trying to create an environment that will create the unexpected or engender the unexpected. I could go into a long soliloquy about how much the unexpected has been important in the last 100 years of science, but I won't do that right now. Well, thanks very much.
Thank you, Gene.
To bring this back into perspective with respect to space medicine and space biomedical research, I would like for Jeff Sutton to make a brief presentation. It's 5 minutes long, and then we'll have a brief break, and then we'll go on over to the Collaborative Research Center. But this is Jeff's presentation will fit very nicely with the aims of the RISE Collaborative. So, Jeff, would you?
Thanks very much, Dr. Alford. I'd like to just follow up on Gene's nice presentation and his comment about NSBRI seeking to have space within the new Biosciences Research Collaborative, which we're very excited about. Indeed, that's true. We are looking at a project, a consolidated research facility. It's a project that's not been completed, but we have made a lot of progress and are very close to completing a deal. Formally, it's a collaboration between the National Space Biomedical Research Institute, the Center for Space Medicine at Baylor College of Medicine, Rice University, and NASA. And of course, that collaboration extends beyond those entities, because when you look at NSBRI, it itself is a collaboration among about 60 universities, formally governed by 12 institutions, with a lot of collaborative activity with the internationals. So we're really looking forward to this being a very open and conducive environment for scientific research pertaining to space biomedicine and to space medicine, and a place for education and for a host of other activities really to be defined by the broad user community. So we've had some fun thinking about concepts and design. We've tapped the advice from multiple people, and we think that it's very important that NSBRI, that's been a virtual institute for its first 13 years of existence, really does have a physical home, has a center with resources that complement nicely the resources that exist within the recipient institutions at NASA and collaborators. And so we looked for an open workspace environment, looked at reconfigurable laboratories for demonstration purposes of countermeasures and other technologies. And we looked at some wet lab capabilities and group meeting spaces, and really a front door that expresses a very pleasant visual aesthetic. And with that, I'd like to show a brief video. It's 2.5 minutes, and then that's the end of my presentation. It's a schematic put together by an architectural firm that we worked with. There are no people in the actual little video, but that's going to change. Hopefully, I hope you enjoy it, and I'm not responsible for the music in the video. Just want that to be a disclaimer. So if you could show that little brief video, that would be wonderful. So these are the demonstration laboratories to be used on a rotating basis for different groups to come in, collaborate, and work together. Different offices and open areas for collaborators and international collaborators to come, special visiting scientists. Okay, thanks very much.
Let me just briefly tell you, we're going to exit the building here in a few minutes. There's a brief break, and you go down these hallways on either side of this room, and there's an exit door at the back of the building, and there'll be some buses there to take us over to the Rice Collaborative Research Center. And then we'll come back here after that. There'll be a meeting at first in the auditorium there on the first floor, where, as Jean explained, they will describe the center physically, and then we'll split into 3 groups and just briefly make a walkthrough of some areas that have been selected. And Jean, thank you for your presentation. So we have a brief break, and we wanted to do this at 4:20. Yes, sir. That's what they said. The back part.